All right, I'm going to walk you through one more worksheet because I'm going to be gone at a conference. But again, if you're homesick, this will help you out. Now, for whatever reason, when I turn this into a PDF, all of my arrows did not work. So see all these boxes? Just pretend they're arrows, okay? So here is a reaction. We do not know how this occurs. How does this become that? Well, scientists create what we call mechanisms, kind of a play-by-play action as to what we think happens. Then they do a bunch of experiments and they back it up, all right? So catalysts, their job is to lower the activation energy. Remember, we've looked at energy diagrams, okay? And every reaction has a hill it has to get over. Catalysts make this hill smaller, so it makes them go faster, okay? But this reaction is thought to take place by the means of this mechanism. So this plus this becomes that, and then that turns into those, and then that turns into those, okay? Notice this is fast, this is slow, this is fast. So let's tackle a couple of vocabulary words. Let me get rid of some of this mess here, okay? Vocabulary words. Intermediates. An intermediate is made and then immediately used. So it's going to be a product and then a reactant. So do you see how this is made and then it's immediately used? That is an intermediate. Do you see how this is made and then immediately used? That is an intermediate. Now, catalysts are a little different. A catalyst is something, if you have one, it shows up at the very beginning and it shows up again in the end. But it doesn't actually get used up. It's there in the beginning and it's there in the end. So there's your catalyst. All right. Another catalyst is discovered which increases the rate of only step one. Does this affect the overall reaction? Well, step one is already fast. Making it faster really isn't going to make a difference. It's like if you're in a swimming race or in a track race, you're only as fast as your slowest runner. So if everybody else gets incrementally faster, but the other person doesn't, your whole team is not going to get that much faster. It's really not, okay? Which step has the greatest activation energy? Well, again, that is that hill. Isn't the slowest step going to have the biggest hill? Yep. How many bumps will be on the potential energy diagram? So again, we're talking about a diagram like this. Well, for every step, you will have a bump, okay? Every step has a bump because every step has an activation energy. So this particular one will have 3 bumps. The rate determining step, the rate limiting step, that is also known as the slow step. So you should be able to answer that question. And we've talked about this. In order to have successful collisions, particles must collide with enough energy in the proper, fill in the blank, starts with an O. I know you know it. Now, let's come down here and let's actually draw this one out. On the set of axes, draw the shape of the curve you might expect. How many bumps? 3. Remember, we said that we're going to have 3 bumps. And it's exothermic. Well, what does that mean? Exothermic means energy is going to be given off. That means you're going to have less energy in the end. So we need to start high, we need to end low because you're going to result in less energy. You're going to get rid of it. You have to have 3 bumps. But which bump needs to be the biggest? Well, the slow step. So you're going to have something like this, followed by this, followed by this, something like that. What am I looking for? 3 bumps, and the middle one is the biggest, okay? And you don't need to do this in the drawing tool unless you're doing it online. I do have paper copies available for you, okay? So here's another mechanism. Again, those should be arrows. How do you get the overall equation? Well, guys, this is just algebra. If something is on this side and something is on this side, they're going to cross off. So do you see how that crosses off? And that's going to cross off. All right, so what do we have left? O3 plus O makes 2O2. At least I think I did that right. I hope so. All right, now I'm going to erase that just so we have some room here. So the next question is, what could the catalyst be? Go back and look at what I said earlier. Catalysts appear in the beginning and they appear at the end. An intermediate is made and immediately used. So go try those. okay? The rate of a reaction is identical to the rate of the slowest elementary step. So we're going to find reaction rates a couple of different ways. One is through data analysis, and it's fun, but it's not necessarily difficult. This is the other way. If you know the slow step, you can write the rate law right from the slow step. All right, and I'm going to show you how to do that. So the first things first. Above, determine the net reaction for both. So come up here, if they show up on both sides, cross them off, combine. Now some kids get confused. How do I combine this? Well, guys, that's going to be two O3s, right? Three O2s. I'll let you do this one. Intermediate is made and then used. So yes, there's intermediates in both. Find them. What is the molecularity of the rate determining step? Let me erase this so we have some room here. Okay. Molecularity of the rate limiting step. So I want you to focus on the slow step. Molecularity is how many molecules are reacting. Well, right here, how many molecules are reacting? One. So we say that it is unimolecular. And if you look at the slow step here, how many molecules are reacting? Two. So we would call that bimolecular, all right? A rate law is always going to take the same form. Rate equals some constant, concentration of, I'm going to pretend we have an equation here. A plus B makes C, okay? A to some exponent and then B to some exponent, all right? If you have a mechanism, you can write the rate law right from the slow step. So for mechanism 1, rate is going to be K, concentration of O3, because that's your chemical. And how many are there? Well, there's just one. You can write the one or you can just leave it, all right? For mechanism 2, there's only going to be one change. It's still going to be rate equals K, but what are you going to write for that exponent? Well, guys, isn't there 2O3? That 2 becomes your exponent, all right? Now, the experimentally determined rate law is that. So which mechanism is probably the correct mechanism? Is it this one or is it this one? All right, that should be easy to answer. Note, a mechanism must be consistent with experimentally derived data. Just to let you know that. All right, so here you are going to do some practicing. I am just going crazy today. Write the net reaction. So make sure you cross things off, add it up. Write the rate law. Guys, use the slow step. Don't use the overall net reaction. Here's another one. Find the net reaction, cross off things that are on both sides. When you write the rate law, use the slow step. And then there's something called orders. So we have zero order, we have first order, we have second order. I'm going to write just really, really plain things here just to make this make sense to you, okay? What does that mean? And then rate equals Ka squared, all right? Let's say we have A, and A goes from 1 molar to 2 molar, all right? And then we have the rate. And let's say the rate is 5, and then the rate is 5 again. So what you want to do is you want to look and go, well, the concentration doubled, but the rate, 5 divided by 5, stayed the same. How do you make this equation be true? Well, you need to add an exponent of 0. So we call that zero order. Zero order does not change the reaction rate. Does not change the reaction rate. You can dump the entire box in and it ain't going to change, okay? So zero order just means that it has no effect on the rate. So we don't even include it in the rate law. We just don't include it. All right, what does, let me change something here, all right? 5 and then 10. So what does a first order look like? Well, let's go back to this example, all right? The concentration doubled. 10 divided by 5, always do big number divided by little number. The rate doubled. Well, what exponent makes this true? 1. What does it mean? What does a first order reaction mean? It means if you double the concentration, the rate doubles. All right? So let's try one more example. I got to think here, you guys. My brain is not working. Let's do 2 and then let's try that. Okay, sorry. I'm not thinking too well. It's like a Monday in disguise. So let's try this one. Well, the concentration doubled. 16 divided by 2 is 8. Okay, I lied. This isn't going to be a second order. It's fine. How does 2 become 8? Don't you have to cube it? So this would be what we call a third order. Third order means that if you double the concentration, the rate triples. So I suppose if I would have put an 8 there, 8 divided by 2 is 4. How do you make 2 into 4? You square it. And that's a second order. So again, zero order just means that it has no effect on the rate. First order means if you double the concentration, you double the rate. If you tripled the concentration, you would triple the rate. If you quadrupled the concentration, you would quadruple the rate. For a second order, if you double the concentration, then the rate quadruples. Okay, it goes up by a square factor. And we'll get more into that, so don't worry too much about it now. We will have a big discussion about that later on. Now, go try this worksheet.